Hello, everybody, and welcome to the fourth installment of the 272 CAD course. My name is Phil Seminowski, and I will be running the course. Emily, would you like to say anything?
Hi, I'm Emily. I just graduated from LC, and I was on Team 272 for 5 years.
Perfect. So today, I don't actually have a presentation, but we are going to all open Onshape and start learning about extrusions. I find that even if I did do a presentation, it's usually not as good as me just showing specifically what extrusions and revolves and other features do. So that's kind of my plan for the day. So give me a second. I just need to log in, and I'm going to open up that document that I created. It's just my name, and we're going to start making some stuff with extrusions. Does anybody have any questions before we jump into it? All right, cool. I'm going to share my screen. And off we go. So let me get to a blank part studio here. So I'm going to make a brand new part studio and start from scratch. And I'm going to start with really, really basic shapes and extrude them to give you an idea, to give everybody an idea of how things work. And the first one that I start with, because it's generally the most used feature to make a 3D object, and that's called extrude. Extrude is basically, if you could imagine, it's like taking a 2D shape and pulling it up into space, and it makes exactly that same shape. So if anybody ever played with Play-Doh when they were a kid, and they had those like Play-Doh things that had, you put the Play-Doh in the backside and it had a specific shaped hole, and you push the Play-Doh through, usually like with like some kind of plunger thing, and it came out in that shape continuously out of the Play-Doh. That's basically what extrusion is. Or another good example is like cake decorating. You know, the bags that they have the little things in the end that have different shapes. When they're decorating the cake, those are extrusions. They're extruding the cake material out of there to make that specific shape. So we're going to do that, exactly that, within CAD here, and that is the feature that is by far used the most out of anything in CAD. So I'm going to start by, let's see. Today I'm going to make a real-ish robot. I'm going to design a little bit of a robot, okay? I'm going to start on the top, and I'm going to use some of the other things that I've been teaching throughout this course, such as variables and other things. And I'm going to start out with just a simple frame. It'd be a center point rectangle. And then I'm going to use the offset feature to offset all 4 lines here by a specific amount. I'm going to hit enter. I'm going to change that to 1 inch. And before I start the sketch, I'm going to make 2 variables. So there's a variable up here, and I'm going to call this length. I'm going to give it a value of 30. And then I'm going to make a variable called width. Make it a value of 22. I don't know. Just throwing out numbers. We can change these later. So now we can take these 2 numbers and use them later in other features and sketches. So let's see, where's the front? The front is that way. So I'm going to dimension. Where's my D key? There's my D key. This is going to be # length. So does everybody see I'm utilizing that variable length, and it automatically is going to make it that value.
I have a question.
Yep.
How do you make a variable again?
Yeah, let me show you. It's variable is a feature when you're sketching. Variable with, I'll show you in just a second. You can also make them as you're sketching. Like I can sketch and I can type that # and I can make a new variable and it'll automatically create a variable for me. But if you don't want to do that, before your sketch, there's a feature. It looks like an X in parentheses. And Vihan, it's okay. We went over this in the last class, actually. So it's totally understand that you don't know what that is. And that creates a feature of a variable. Now, for a little demonstration purposes, if I take this width variable and I click and drag it below the sketch where that variable is used, remember this tree over here, this feature tree, it's a timeline. Things happen in chronological order in that timeline. And so what happened here is the sketch is looking for the variable width, but it doesn't exist yet. I haven't created it. So the sketch is unhappy. And now if I open that, it's going to be like, well, what is this variable? It doesn't know what this number is. So you have to make sure that when you create variables, you create them before you utilize them. So we created that 22 and that 30. And now if we wanted to, I can come and double click on length here. And let's say 30 was too long. We want to make it 28 inches instead. Now it automatically adjusts that value to 28. And this is really good for stuff like this, especially at like the beginning of a robotic season. Making easy, quick, like wholesale changes to the size of your robot is a huge benefit. And you can do this just by editing the sketch and editing this number. But what using a variable allows you to do is change it on the fly, but then also to update that variable. So maybe you want to put or use that variable in other ways. Maybe we want to put a crossbar in here that's like halfway from the back, or like a quarter of the way from the back of the robot. We can do variable length times 0.7 or 0.25. And that will, no matter what the value of this number is, it will always be a quarter of the way from the bottom edge. So if instead of 28, if I put 30 in there, and I show you the sketch, it recalculated that value to be 1/4 of whatever the value of length is. So this is where we can start to utilize math in building and designing our robots and other things that we design. Anybody have any questions about that? All right, cool. So I'm going to start off with this as a frame, and we can always come and change it. And I'm also going to start a sketch from the side. We're going to make a sketch on the right plane. But before that, I'm going to make one more variable, and it's going to be called wheel B. And I'm going to call this the diameter of the wheel. You'll see how we utilize this in a second. And let's set it to 3 inches to start with. So generally speaking, I would start a sketch from the right. And right now, swerves seem to be the most common drivetrain. But once upon a time, tank drive was very much the most common and most effective drivetrain. This is well before swerves were a thing. So for today, I'm just going to draw a tank drive, and I'll explain what's going on with that. And really, I'm just using this to show you how you can get a general rough kind of dummy shape of your robot. I'm using this as an example of how to use features. I'm not using this as this is how to design your robot. I'm doing it in combination with this is how to use features, and this is maybe how you would go about designing a robot. So wheels are generally round, and generally in a tank drive, you'd want your center wheel to be directly above the center of the robot. And remember, I created this wheel diameter value, right? So I can take this and dimension it and have this be wheel D. And that will make the diameter of the wheel 3. And I'm going to make another wheel over here. And I'm going to click the first wheel, or click the second wheel and click the first wheel. And we're going to use the equals constraint, because I'm assuming we don't have 3 different size wheels or 2 different size wheels. We want all of our wheels to be the same diameter, no matter what, basically. And normally you'd think, oh, you want to put this wheel directly on the flat surface. Well, when you're dealing with a skid steer robot or a tank drive robot, what happens is if you have all 6 traction wheels on the floor at the top at one time, and you have a thinner robot rather than a wider robot, the front and back wheels will actually work against your rotation. They will cause a lot of friction when you try to rotate. Like imagine trying to take your car and trying to rotate it in place. Like it'd be really difficult, right? And the wheels would squeal and everything. That's kind of what we try to avoid by doing this, and that's raising the outer wheel by a little bit. And I'm going to show you how I would sketch that. I'm going to draw a line from center to center on these so that later we can determine how far the chain spacing needs to be. We'll talk about chains maybe later today. And then I'm going to draw one more wheel over here, make these equal to each other as well. Equals. And I'm going to do one more thing. I'm going to make this wheel symmetric in position to this wheel based upon the front plane, which the symmetry constraint is right here. So now when I move this wheel, it moves the other one. So there's symmetry about that front plane. Anybody have any questions about where I am just yet? All right. Another thing to note is I made this line dotted, and that means construction. The button for construction is right here. It's a solid line and a dotted line with 2 arrows pointing to each other. Construction, basically geometry, construction sketches, and construction points and curves don't allow you to use them for generating solid features like when you extrude or when you revolve. They only give you the line between the 2 points, the curve, just as a reference. So at a drop center wheelbase, you generally want the center wheel. So I clicked on the wheel, on the bottom of the wheel, and then the top plane. It's not going to let me choose the top plane. Top plane. And I'm going to dimension those, and I'm going to make it 1/8 of an inch. What that's doing is the center wheel is 1/8 of an inch lower to the ground than the 2 outer wheels. Okay. And remember early in our first thing we said we should always design things as if they're centered on the origin, which our robot is right now, and that the wheels are on the ground, or whatever we're designing is on the top plane, which is exactly how I'm designing it right now. So now we've got 2 wheels that are exactly 1/8 inch off the ground, and they have some center distance to them each, and I can draw one more line between this wheel, even though those lines are the same length. Make it construction geometry. And we've got our frame that exists. It's kind of hard to see, but right there. And click this point and this line, and this is kind of a unique constraint. It's called pierce. It means that you have a line that cuts right through a point like that. So I set it up so that my line in a different sketch plane pierces directly through the point. If that's confusing, that's okay. It kind of is. And then I'm just going to use this as construction geometry. And then I'm going to draw a frame somewhere in this vicinity that it's going to be reminiscent of what our actual frame will look like. So the material that's typically used in FRC is 2x1 rectangular tubing. So I'm just going to draw like that right now. And then I could center this rectangle on the center wheel, or I could line it up with the outer wheels, but we kind of want to split the difference between the two. So I'm going to put a point at the center of this line. And this line is on a slight slope, right? Like if I take a dimension from here to here, the distance between that should be that same 1/8 of an inch. The same as what we did here. And if I change this to 0.25, that becomes 0.25 as well. Do we see how this number is like grayed out? When numbers are grayed out like that compared to when they're solid, that means this is just reading the number. It's not defining the number. It's just telling you, hey, the distance between this point and this point is 1/8 of an inch. It's not telling it that it has to be 1/8 of an inch. If I told it that it was going to be a driving dimension, it would say, oh, we've got a problem. I have two dimensions telling me to be two things, to be two different things. That's a problem. We can't have that. We can only have one dimension. So that's the reason why that shows up as a gray dimension. So if we wanted to find the vertical position of our tubing, I would take this center line here and line it horizontally up with the center of the frame. And now we've got the height of our tubing, of our drive rail. Now, maybe it seems like we don't have a whole lot of ground clearance here for our wheels. Like, what is that? That's not very much from here to here. Oops. The bottom of the 2x1 to the floor, we only have just over 1/2 inch of ground clearance. That's not a lot of ground clearance. So maybe 3-inch wheels aren't going to do it. Maybe we have to skip the 4-inch wheels. Well, now that we created this variable, we can go in there and instantaneously change the 4-inch wheels, and it automatically updates this whole sketch for us because of the way that we constrained the circle to the point, the way that we constrained the tubing to the center line between these two, so on and so forth. It kind of does all the math and all the tricky stuff for us. Does anybody have any questions yet? All right, cool. And then I'm going to do one more thing. I'm just going to dimension some nominal number between these. Should be dimensioned on an angle. It is on an angle. There we go. 11. 11 seems fine. Maybe 12. You do have to remember that there's going to be tubing like this too. That is 1 inch. Maybe 11.5. Cool, that looks good. All right. So I'm going to finish that sketch, and now we've got these two sketches where it doesn't really look like a robot yet. We can use these two sketches to build kind of the major components of a robot. In order to create this surface, there's a few different ways that I could do it. what I'm going to do is extrude this, 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 and this. I should really make all those wheels. I'm going to make all the wheels construction geometry, actually. And this construction geometry. There we go. I just made all the wheels construction geometry. I'm going to extrude this box up to a vertex. I'm going to select this vertex. And the reason that I'm doing up to a vertex, actually, let me walk through what I just did. So let's talk about extrusions for a little bit. Extrusions, as you can see, take the profile, the shape that you created, and they extend it some distance. And that distance can be defined by a number of things. And that's what this drop down gives you options to do. So blind means that you could just set the distance that you want it to go. Like you could tell it exactly 6 inches or exactly 4 inches or whatever. Blind's probably the most common one that's used, but you want to make sure you use the right one so your models kind of automatically update. The next one is called up to next. So if I had another object that was behind this, I was like over maybe in this area, it would extrude up to that object, and it wouldn't care about any of the curves or any profiles on that surface. It would just extrude all the way up to it, and maybe I'll give an example of that. I'm going to edit this sketch just so that it has a little weird object over on the side, for an example. And I'm just going to extrude that sketch alone by 10 inches. I made this weird profile, right? So I'm demonstrating what extrude up to next does. So instead of blind, you see how blind, if I do 1 inch, and then I can do 2 inches, and I can do 3 inches, 4 inches, 5 inches, so on and so forth. I do 20 inches. Then these two things intersect. And it seems to automatically want to merge these two parts, but maybe I want to keep them separate. If I left them like this, I don't know what its issue is right now. I don't wish to merge. Oh, it's because it's on add. So add will add two parts together, and you have to tell them which parts you want to add together or not. Instead of new makes an entirely brand new part. So these will be two independent parts rather than one merged single part. And that's an important distinction. And where you want to separate is when I make this object, what components am I going to need to make it, or what is the raw material that I'm going to use to make it? And we're going to talk about all that kind of stuff later in later portions of the class as well. So for now, I'm going to do new. And this is what happens if I just do a straight extrude as a blind depth, 20 inches. It'll just make a new object. It'll be basically like a rectangular object. I can hide the first part. But if I did instead up to next, you can see it totally changes the shape of the part. It actually now contours to that other part that we made, right? So maybe I do want these parts to like interlock and mesh with each other. If so, I could use that up to next. And the cool thing is that anything that I make changes on this part, it's like if I change this extrude, if it now has a taper to it, which is known as a draft, maybe it goes like this, some kind of base for something, and it tapers out. If I did that instead, my part that I made previously, it follows that same profile still. It still has that angled cut because we told this extrude to extrude up to next. All right, cool. So now I'm going to delete that, and it's going to yell at me, and I'm going to edit. I'm going to edit that extrude that we were just in and messing with. So instead of up to next, if you did up to face, I could select any face or a plane or something, and it would extrude up to that plane. If I did up to part, I could select any individual part, and it will extrude out to that part. Kind of like up to next, but only for one single piece. And then what we're going to use is up to vertex. So I'm going to use the corner of our drivetrain as the vertex to extrude to. And you'll notice that only goes one direction. So what I'm going to do is I'm going to do a second end position, and that's going to extrude it the opposite way, and do the same thing up to vertex and select over here. Another option is you could just mirror the first frame piece that you make. So I make that shape. And then I've got this surface that I could extrude away. So instead of a new extrude or an add extrude, I could do a remove extrude. And I can cut away material from things. So I have the remove, and I selected through all. So it's going all the way from where the extruded start all the way up into infinity and removing anything that runs into it from part one. And that kind of creates our dummy little, our little simple frame here. Any questions up to this point? I know I'm going pretty fast, and I apologize. I'm more so just trying to demonstrate how features work. And I'm just trying to use that with designing a robot. Now, this is all shown as one single piece of tubing here. Maybe we want to split that into different pieces. And maybe, like the front and the back pieces, it seems like they're going to be about the same. So maybe we don't need two separate pieces for that. But another feature that you can use is called split, which is right here. And split will take your frame and choose which part you want to split. And then you choose which surface or face that you want to split it on. So you'll see these lines just showed up here. And that's because when I ran the split feature, it now separated our part into this part that kind of looks like a U and this part. So they're now two separate parts, even though I made them at one time. And now I can go back and edit the split feature and do this surface as well as if I want. I don't know if it does two surfaces. I guess it can only do one surface at a time, and that's okay. So you can choose what to split and what ways you want to split it. So maybe I just want to do a second split. This guy on this face. And so now I end up with 4 different parts, 2, 3, 4, instead of the 1. And now those kind of look like 2x1 tubing or something thereof. I'm going to delete this part of the sketch. Might be confusing to people. Select, delete. All right, any questions up to this point? Any confusions about extrusions? You can extrude new, which makes a brand new part. You can extrude add, which adds to an existing part. So you need to have at least one part in existence to be able to do an extrude add. You can extrude remove, which will remove any material in that area. Or actually, my favorite interesting one is extrude intersect. And I'm going to explain that right now with one extra sketch on the top plane. I'm going to make a circle. It goes like this. And if I use Extrude Intersect on this sketch that I just created through all in the opposite direction, and I'm going to merge it with all the parts, you can see exactly what it does. It leaves only the material, only the pieces that intersect with the circle with the original extrusion that we made. So if I did an extrude new, it would look like this. If I did an extrude remove, it would look like this. I would cut away all the internal pieces. If I do extrude intersect, it keeps all the internal pieces and cuts away the corner pieces. Does that make some amount of sense to everybody? I think you can react with hand signals, can you? Oh, it's just a hands up. Just like a question. Got it. Okay. So that's extrude. Lots and lots of cool things you could do. You can also do symmetric, where it will do the same extrusion in both directions. Maybe I don't want through ball. Maybe I want blind. 10. So it will extrude the object evenly between the sketch plane. Half of the object will be above the sketch plane, half the object will be below the sketch plane if you use symmetric. And then you can also do draft. Draft will put an angle on the object relative to the sketch plane. So this is a 10-degree angle from the extrusion, so it's going out 10 degrees. If I did 45, it'd look like this. Maybe we're making a giant yo-yo. I'd be willing to bet this is just about how yo-yos are modeled. And then add, if we did add, it would add these two pieces together. It would add the frames, and it would add this new giant yo-yo piece. And if we did remove, it would remove all the material that the yo-yo piece takes up from the other four pieces. So we'd be left just with this. And if we did intersect, you'd only be left with the material that the yo-yo piece intersected with, like this. So it might be a bit confusing. That's okay. And there's a lot of different options and a lot of different weird things that happen. But hopefully that was a little bit, it helped you understand how that shape was made. Does anybody have any questions about extrusions? All right, cool. It's 8 o'clock. Let's make an object with extrusions. So I would like everybody to go into their document, start with a new part studio, and I'd like you to pick something up off your desk. And if you can, turn your cameras on and show what you're going to model. It could be a stapler, which I know aren't very exciting. It could be your phone. It could be like if you have a bottle in front of you, or a glass of water, or if you have a book, or if you have even your keyboard. Keyboard would be a pretty crazy one. Or like this. This is like an armrest for my thing. Grab a fairly simple object if you can, and show it to the camera if you're able to, and take your best try at modeling it. Try to do it with extrusions only for now. So if you do know other features, we'll hold off on that. And if you don't know what to model and you'd prefer me to give you a specific thing to model, just let me know. So what's everybody choosing? Grace, you have any idea of what you're going to model? Vihan, do you have any idea what you're going to model?
I'm going to model this little radio thing.
Perfect. Absolutely perfect. Christian, any idea what you're going to model?
I'm going to model my phone.
Cool. Perfect. Grace, how about you?
I was gonna model my phone too.
Sweet. And Mr. Pingu, who I forget your actual name.
It's Brent.
Brent, that's right. Brent.
Yeah, I don't really know what to model.
All right,
I
go ahead.
I mean, I can do my phone, I guess.
You're more than welcome to do your phone. I think phones are a pretty good, simple thing to model. If you want a challenge, try to model like the buttons on the side of your phone, right? Like I have a little volume and power buttons on the side. And maybe you can just model like if you have a camera bump out like that, or I have a little fingerprint scanner here. Maybe that guy.
Yeah.
Maybe put the hole in for your charger. I have a charger port hole on my phone there. You could do that.
Yeah.
So those would all be good features that can all be done with extrusions. So let's take a stab at that. Would it be helpful if while you guys are doing that, I'm doing the same with my own phone, just to show you where I might start? Would that be helpful at all?
Yeah, I would.
All right, perfect. And so you guys work, and I'm going to model. And if you want, you can keep up with me, or you could just start to model on your own. So I'm going to create a new part studio, and I'm going to call it phone. I don't know the exact size of my phone or anything, but I know my phone is roughly rectangular. So I'm going to start a new sketch on the top plane and draw a center point rectangle. And this is where you might want to put dimensions if you want to change the dimension of your phone later. I'm going to say it's probably close to 6 inches by 2.75 maybe. That looks about right. I'm actually holding my phone up to my computer screen to see if the proportions are right. So, which you guys are more than welcome to do as well. Maybe 3. Because what's plotted on your computer screen is actually 1-to-1 proportional. So if you zoom in or out a little bit, you can put your phone up to it and see if it's the right proportions. That's about right. I'm going to finish that. And I'm going to extrude it by 1/4. And then let's see. Got these corner radiuses. Bonus points if you use like mirror or something, because there are usually lines of symmetry on a phone in some way. Maybe it's a little bit bigger than that. Point. Let me do a radius here too. 0.25. 0.2. All right, we're going to do that for now. And then on the back of the phone, the model. Also, use the internet. So, like for example, you could look up the actual dimensions of your phone. This, if you know what kind of phone you have, you could look up the real actual dimensions of the phone. and you could put your phone like into scale real life in CAD here. There's actually people that sell models of things like phones that they make in programs like Onshape for money. Like they'll model something and then they'll put it on a public website where people can buy that model and use it in like animations or in, you know, renderings or stuff like that. So I'm going to look up what the size of a USB port, the C port specifically. Looks like it's 8.4 by 2.6 millimeter. By the way, in Onshape, you can straight up draw or sketch things in. You could type in dimensions, millimeters, or the units, and it will automatically adjust those units. I'm gonna take this line slot out of it. And they are 8.4 by 2.6. Oops. 2.6. And 8.4. Looks like the USB port. Assuming the USB port's halfway up the phone. I'm going to extrude, remove the USB port, I don't know, 0.25. I don't know how deep they actually are. A little bit deeper than that. And my phone looks like it has a little bit of a bevel on the top as well. So I'll do one here that is a tiny bevel. Cool, that looks nice. And then if I wanted to do the power and volume buttons, I'll do a new sketch on the side. And power, volume buttons, I believe, are the same size each. Make them equal to each other. Equals. And these are all going to be in line with each other. Coincident. They're all going to be centered on the phone. And this one's going to be, I don't know, 0.375. They're going to be 0.125 apart. That looks about right. And this one's going to be a little bit smaller. It's going to be a little bit further apart. And that's going to be some distance from the center. Each one of those are going to be a slot. That is 1 divided by 32, maybe? That looks too small. That looks about right. This and this are going to be equal. This is also going to be a slot. Dimension is going to get deleted. Equals construction. Cool. Extrude that. I don't know. They only stick out a little bit. 1 divided by 32. Sweet. I'm going to do my camera bump out thing. New sketch on that surface. Rectangle. It's about square. Make the two sides equal to each other. Click and drag it and put it at 0.75. Some distance from the center. 0.65. And some distance from the center from above. 2. 2.5. This 0.75. I'm going to round these corners. Oops. Extrude. Camera bump only sticks out 1/16 of an inch. It has radius on it. It has a smaller bevel on the top. All right. I'll do one more. If anybody's having any major struggles, please stop me and let me know. I'm going through mine quickly just so I can show people who are watching now or who are watching in the future how I might go about drawing these features. But I do intend to help everybody here in class with what they are drawing. Just give me a few minutes to finish up mine and I will come and help you. I'm going to extrude remove maybe 1/16 of an inch from my little fingerprint scanner, and then I'm going to radius this corner by 1/16. Beautiful. That's about what my phone looks like. Maybe that's too deep. Divide by 32. That looks about perfect. I wonder if I send my if I send this model to Google and they'll be like, "Hey, stop stealing our phone designs." Nice. All right, so that's how I would make a rough model of my own personal phone. Now everybody's phone's got a few different features, a few different odds and ends, and you could probably add some more extra things or make it the right color or put different materials on it. Would anybody like to share their progress, or is anybody having trouble modeling something or having problems sketching stuff? The only features that I used in here were extrude and fillet. And I did not go over fillet, but fillet makes rounded corners. So if you have a sharp corner, it will round it off. So I only used 2 features. And in my sketch, I really only used 3 sketch features. And that was a rectangle, a center point rectangle specifically, and a circle, and then slot. I did use the slot, which I made a straight line, and then I made a slot out of a straight line. And that makes kind of like a oblong circle, like if you took a circle and like stretched it. So would anybody like to share where they're at or what struggles they're running into? All right, then I'm going to start picking on people. Let me see if I get this name right. Brent, is it right? Is Brent right?
Yeah, that's right.
Perfect. Awesome. All right, Brent. Can I see what you got so far? Can you show
Yeah.
everybody?
How do I
I'm going to stop presenting and then you'll be able to share.
Oh, okay.
It's an arrow up in a box.
Oh, present now.
Yep.
Do I
You just got to click which screen you want to present.
I don't know the difference between these ones. I guess I'll do tab. Oh no.
I usually do my entire screen.
Okay, I'll just do that then. I did my phone and I tried to add like the
Oh,
the camera
nice.
kind of. And
Nice.
I didn't really have time to do the like the volume buttons, but I did add the charger port here.
Nice. Fantastic. That looks awesome. And as I could see, you used only the extrude and chamfer and fillet features, right?
Yeah.
Yeah, so that's a really great example of how simple how you can make really interesting shapes and content with just a few features. Most of what we'll be doing when we're building robots is actually extrudes and fillets. We're going to be using holes as well, and probably some revolves for shafts. But the majority of our features will be likely extrudes and fillets and holes. So that looks awesome, Brent. Really.
Okay.
Very impressive. You're picking this up quick. Wait, I forget, did you have experience with CAD?
No, this will be my first time.
Excellent. So you're really picking it up very quickly.
Okay. Thank you.
All right. I'm going to switch over to Emily. I don't know if you've been following along. I know you mentioned to me that you would be looking at some of the videos for stuff. It's okay if you're not. I'm just picking on people.
No, sorry.
All good. Christian, would you mind sharing your phone or I forget if you modeled your phone or something else that you had.
I'm all on my phone.
Perfect. Would you like to share that?
Yes. Oh, shit. How do I do that? Yeah.
When you're in the meeting, it's a little box that has an arrow up that says present now. And you could just do your whole screen and share your screen. Or a specific window if you want.
Hold on. I'm trying to figure that out.
Take your time. Take your time. Is anybody here working on a Chromebook? I've had mixed results with Chromebook.
Yeah, I am.
Okay. Let me know if you're having trouble like running things or if it seems slow or laggy.
It just won't let me share my screen. Like I see it there, but it won't let me click it.
Yeah, I'm not sure how I can help you. So you can't click the present now button?
I can click that and everything else, but it just won't let me share it.
Okay. No worries. You might just pass on you for now. Keep trying, and if you can get it to share, let me know, but don't spend too much time, all right?
All right.
All right. I'm going to pick on Vihan now. Where are we at?
So I'm trying. Pretty slow. Trying to make my.
You don't
Well-
need to apologize or think that you're very slow. Remember, I've been doing this for like 15 years now. So if I seem like really fast and it seems scary how fast I am, or if you can't keep up, no shame whatsoever. Tell me to slow down. If you don't understand the buttons I'm pressing or where I'm going, please just mention it, and I'll do my best to slow down. So I apologize if I do go too fast, but you're not going too slow. There's no such thing as too slow. Just go at whatever pace you can and get whatever done that you can. You'll figure it out over time.
So as I was trying to make the little. Can't see myself right now. I was trying to make the little vents here, I guess I should call it.
Yep.
So then I was trying to make it there.
That might be a good use of that feature that I was just telling you about.
The fillet.
Remember, not the fillet, the slot feature. Let me go over that one more time. So if you look at my screen, I'll share my screen for a second if that's okay.
Yep.
So the slot feature in Sketches is really, really helpful. I'm just going to make a new thing over off to the side here. Make a new sketch. So a slot is basically you can draw any line anywhere like this. If you click on the line and then click this button right here, it's called slot. It's right next to the offset button. If you don't see it, it might be underneath the offset button. If you click slot, it'll automatically make that rounded shape around the line.
Cool.
And
Oh, yeah.
and now you can change this distance. Maybe we make it 1. And then all you need to do is dimension this line to be whatever length you want, or and then whatever positions that you want this to be in.
Cool.
So that'll save you a lot of time sketching all 4 individual pieces of those slots. Also, keep in mind that they're symmetrical. So see if it might be helpful to use a plane of symmetry instead of sketching the whole thing. But yours will look something like this. You'll draw a horizontal line and then another horizontal line. And what you might want to do is a line of symmetry. It'll be a dotted line like this. And then you can mirror the other 2 lines about that line. So I know I did that quickly, but let me run through that again. Do you see how these lines are mirrored now? Whatever I change on the bottom one, it changes on the top one, and vice versa.
Yep.
Right? So how I did that is I created a line. I created a line of symmetry, which I just made dotted because I'm not actually going to use that for geometry. I made it construction geometry. And then there's a mirror button. It looks like two L's like this with a dotted line in between. All right, that means sketch mirror. Now we can mirror parts as well. Like we can make a right hand and a left hand part, but we're just mirroring in Sketches, which just takes sketch geometry and puts it on 2 sides of a line. So I have this upper line that I want to mirror onto the bottom line. Or maybe, wait, first let's make it a slot. I want to mirror the slot to the bottom. I would select the mirror button, and it pings you, it tells you select a mirror line. And that's the line at which you want the symmetry about. So I'm going to select this dotted line that I just made. And then it says select entities to be mirrored. I'm going to click and drag and select all of that slot. And it'll mirror the slot around the line. And now you've got 2 slots that are exactly the same in every which way. They're just on either sides of that line.
Cool. Yeah.
And now if I change this dimension, 1, it'll change the other dimension. If I change the length, 4, it'll change the length of the other one. And if I change how far this is from the center line, 2, it'll change how far it is from the center line. Make sense?
Yep.
Cool. So you could try that, and that might save you a little bit of time dimensioning things. You could also try to just sketch the one side and actually mirror the feature that you make. So when you extrude, when you either cut or extrude out, you could mirror that feature about some plane in the center. And that might be the way to go. But yeah, that slot feature is super, super useful. And there's so many things with that shape. Slot also works with curved lines. So if I draw a curve like this and I select it, make a curved slot, which this is kind of a pain in the butt to actually sketch. So it makes it much, much easier that there's a dedicated feature to it. That's a huge one.
Thank you.
Yep. Cool. Anybody else running into any issues? Christian, were you able to share your screen at all, perchance?
No.
All right, no worries, no worries. Are you having any trouble with your modeling?
No, I'm not.
All right, cool. Grace, I haven't gotten to you yet. How's your phone coming along? Or whatever you're modeling.
It's happening. It's going kind of slow.
That's okay. Would you mind sharing it? Would you like to share it?
Sure.
Let me stop sharing.
I'm trying to get the volume buttons right now, and I did like the speakers on the bottom and the charger socket.
Oh, that's awesome. That is absolutely awesome. Oh, I see you started that sketch for the buttons at the center of the phone, right?
Yeah.
That's perfectly fine too. The trouble that you might have with that is if you change the width of the phone. So let's say we're like designers and we're designing the phone and we're not just modeling something that already exists, right? Which is what we're going to be doing when we're designing robots. We don't know what the final version of the robot's going to be. We're using CAD to help us determine that. So if you extrude from the center and you just use a blind extrude like you did, what you might run into is now, let's say the phone got wider. What happens when the phone gets wider when it's modeled as you have it?
The extrude isn't really going to be there.
Yep, the buttons will basically be, they'll be subtracted kind of into the phone, right? Like they'll just disappear because the phone got wider. So what you might want to consider is there's an option under there. You see where it says blind?
Yeah.
Click the drop down on blind. Click up to face. And then click on that outside face. Yep. And then do offset distance. And now flip the direction on the offset, which is those little keys right there. Yep. And now what it's extruding now is a distance from that face.
Okay.
And now if your face changes, you will always still be that same distance from that face. Does that make sense?
Yeah.
So now if you put in, you know, like 1/8 of an inch or 1/16 of an inch, and you change the width of the phone, you'll always have that 1/16 of an inch button every single time.
Okay.
Sweet. Good stuff. So yeah, mess with that. Phone looks great. I'm assuming you have an iPhone.
Yeah.
Do they really have a different number of holes on the bottom for the speakers?
Yeah. There's 3 on one side and 5 on the other.
That's kind of weird. I didn't know that.
I
I wonder
think one side might be microphones. I don't know.
I was just gonna say, is one side the microphone, is one side the speaker itself? That might make sense. Cool. That's Absolutely awesome. All right. Is everybody contented with Extrude? We're happy with Extrude? All right, cool. Really good exercise. It's 8:40 now. Next week, we're probably going to get into revolves. But for now, I will likely go and speak about our technical topic for the week. Our COTS. One second, my computer is being very, very laggy. Oh, man. Let's see. I think we're going to learn about gears today, which are some of my favorite. Cool. Oh, where did that go? There it is. All right, let me share my screen quick. Can everybody see my screen?
Yeah.
Cool. Once again, I'm going to use one of those presentations from FRC 3005, the RoboChargers. Again, they've provided these awesome presentations that describe some of the engineering concepts and COTS components that are involved in robotics here. Today, we're going to talk about gear ratios. Now, recall, last meeting we learned about torque, and torque and gear ratios are directly related to each other. So for those of you that have ridden a bike before, especially bikes that have gears, or I should say gear ratios, like different sprocket sizes that you could switch between, you'll know that when you switch to a lower gear, it takes more pedaling to go faster, but it's much easier to go up a steep hill with those lower gear ratios. You just have to pedal more. Conversely, at very high ratios, it takes very little pedaling for you to move a very far distance, but it's extremely difficult to go up hills with those very high gear ratios. And what's happening there is you're trading off distance traveled for output torque. And that's basically what we're going to talk about today with gear ratios. I'm not going to go through all these specific terms, but a good one. So we talked about torque already, but angular velocity is probably a good one to note. Angular velocity is how much something has rotated per unit time. All right. So you've probably heard of RPM pretty frequently, which is how many times something is revolving per minute. But other common ones are degrees per second or radians per second, or there's a bunch of other ones, but usually RPM is what we use. And then we have power, which is the rate at which energy is delivered in the system. It's not the energy. Power is not energy. It is the rate of energy that is delivered in a system. So for example, like let's say it takes 10 kilowatts to power your house for an hour. 10 kilowatts. All right. That means your house uses energy at a rate of 10 kilowatts per hour, which is it's actually power. Kilowatts, that's the measure of energy. Power is the rate that energy is providing. So gears, specifically are used to change the direction of rotational power. Gears actually swap the direction that things are rotating relative to each other. They're used to change the position of rotational power. So if you're providing power here and you want to output it over here, you use gears for that. And they're also used to increase and decrease the speed, and inversely or conversely the torque. So if you increase the speed, you decrease the torque, and if you decrease the speed, you increase the torque of rotational power. But the total power output for any gear train, besides the losses, like the efficiency losses that are done throughout the gears, the total output of the gear train will always remain the same. Now, if you have 20 stages of gears or 10 stages of gears, obviously you lose some of the power to the friction between the gears. But if there was no friction involved at all, you would have the same power output, whether you have 20 stages or a single gear train stage. So the relationship between torque and angular velocity is that the combination of the output torque of the system and the angular velocity describes the power that is outputted from the system. Now remember, power is a fixed amount. Like motors can only provide so much power, right? They're rated by their power. A good example, like a Sim motor or a Falcon motor, has a power rating of, I think Falcons are like 300. Let's look it up real quick. So the Falcon 500 motors have a power rating of 400 watts. Okay, and watts are joules per second, I believe. So measure of energy per unit time. So 400 watts is the max amount of power that a Falcon can output. So what you need to do, when you're figuring out what gear ratio to use, you need to figure out what output torque you want, and if you're okay with that velocity. Or conversely, you need to figure out what output angular velocity you want and figure out if that torque is good enough for it. It's always a trade-off. You always have to decide if you want to go faster and lose some torque, or if you want to go slower and gain some torque. But the power in the system is always conserved. No matter what gear ratio you use, the total power output of the system remains the same. And usually motors produce low torque at very, very high speeds. So when they're running at their maximum speed, they usually don't produce a whole heck of a lot of torque. It's somewhere around like the halfway mark in terms of speed that they're able to provide the most amount of torque. And these that can be determined in what's called motor graphs or power curves. I'm going to find a motor curve for a Falcon. I'm going to pull that over here. And these are just generally good things to know as well, because when we're talking about motors and gear ratios, you want to be able to use the peak power output of the motor, which might not always be the peak torque or the peak speed. So here's a curve, and on the bottom here, you'll see the speed of the motor in RPMs. So you'll see this motor, which is the Falcon 500, has a speed just above 6,000, probably like 6,200 or 6,000. Oh, there it is, just about 6,400. But you'll see at that maximum speed, it provides this yellow curve, zero torque, absolutely zero torque, which means that it's not providing any power at all either. Even though it's rotating really fast, if the torque is zero, you're not providing any power to the system. And remember, that's that equation, power equals torque times rotational velocity. So you'll see when the motor is going about half speed is where its peak power output is. And power is a limiting factor in robots and many other systems as well. So we're trying to maximize this power output usually. So when you spec motors, when you're determining which motors to use and which gear ratios to use, you want to try to size your motor so that it runs at this peak power range. And it can go above that or below that, but that's kind of the Goldilocks range you're looking for. Because of that peak power, it's still moving at a good rate, just over 3,000 RPM, and it still has a really good torque output. It's got, a torque output of like 2.5, which is really solid. So moving back over here, any questions about motor curves at all before I move on? There's a lot going on here. I understand, kind of breezing through it, but it's good information to know and be familiar with when you're designing things. So gear ratios versus gear reductions. They're kind of the same idea. They're just slightly different terminologies, but they're generally a ratio between the input and the output. And the ratio and the reduction just determines which one's in the numerator and which one's in the denominator. So generally speaking, a gear ratio is the number of teeth in the input gear. So on the driving gear, on the gear that's attached to the motor, or the gear that is providing the power, divided by the number of teeth in the output gear. So for example, if you have a driving gear that has 10 teeth, and you have an output gear that has 10 teeth, your overall gear ratio is a 1. But if you have an output gear, or if you have an input gear that's 5 teeth and an output gear that's 10 teeth, then your gear ratio is 0.5, or in other words, 5 to 10, or if you divide it down to its simplest form, 1 to 2. Right? And the gear reduction is just the inverse of that. Gear reduction is the output divided by the input instead. So like I said, these two really mean the same thing. They're just the inverse of each other. But it's important when we talk about these, like this 20 to 48 is talking about the input gear to the output gear. Input gear to the output gear, and generally the input gear to the output gear. And the equations that we use for this, it's actually very straightforward. The speed output of a system is equal to, like the rotational speed is equal to the rotational input of the system times the gear ratio, which is the number of teeth on the input divided by the number of teeth in the output. That gives you how fast your system goes. And the torque is very similar, except for it's not multiplied by the input velocity, it's divided by the input torque. So the input torque divided by your gear ratio gives you your output torque. I'm not going to worry about the math questions here, but you can just generally see that that these do check out. And now we're actually going to talk about gear trains and gears with multiple or trains with multiple gears. The only number of teeth that matters in a gear train, in a single slice of a gear train, like gears that are actually meshing with each other, are the starting gear and the finishing gear. This gear in the center is known as an idler gear, and it does not contribute at all to the gear ratio. All it's doing is transferring torque from the input gear to the output gear. So you want to kind of, if you see 3 gears in a row that are all meshed together, you want to ignore the middle gear and only care about the teeth in the first gear and the last gear. Now, when you have compounding gears like you see here, so you have a small gear driving a larger gear, and then that larger gear moves with another smaller gear. These two rotate. these two gears rotate at the same rate, which is important. And then that other smaller gear rotates an even bigger gear. And these are known as compounding gear trains. So your calculations for ratio are still done the same for the first two. So you have your input divided by your output. And then you could calculate the second gear ratio, which is this input gear, the number of teeth in that, divided by the number of teeth in this bigger gear. And define the overall ratio, gear ratio, from this small input gear here to this very, very large input gear here. You multiply them. You multiply this smaller gear ratio to this larger gear ratio. And that will give you your total gear ratio for your gear train. And do notice that it's multiplicative. So you can have a really, really high reduction over just a few ratios. There's a few really cool gear trains that it's like this artist created a gear train that has like 100 stages of 100 to 1. So it's basically 100 times 100 times 100, 100 times over. And they're rotating the input so fast, and they've calculated that if they rotate it like until a final gear makes one full rotation, it's longer than the entire universe has existed so far. And it's like humans won't even exist basically by the time that happens, that it actually finishes a full revolution. So absolutely crazy things, and gear ratios are super, super helpful in that sense. So let's keep moving on here. You can also have a roller chain, which is like what you find on a bike. Bike chain is another way. And the gear ratio equations work exactly the same way as they do on regular meshing gear. And the same thing for belts. Really, the only difference between them is that roller chain and belts, they rotate the same way. They will always rotate the same direction, whereas gears will rotate the opposite direction. And we're going to talk more about chains and belts later, but hopefully this was helpful. So are there any questions about this? All right, cool. One more thing that I don't think that this went over is calculating the center to center distance in gears. So when you're designing gears, and I'm going to make a new quick part studio here. When you're designing gears, it's really, really important that the distance between the center of the gears is accurate. Gears use a thing called pitch diameter, which is a diameter that goes, it kind of goes like the teeth kind of go like this. Like halfway between the pitch diameter. Not exactly, but about. Okay. So when figuring out this distance from the center of one gear to the other center of another gear, it's very, very critical. And how that works is you just draw two circles like this that are tangent with each other. So these circles only contact at one point, and that's exactly where this line goes through as well. And for the gears that we use, they use a system called diametrical pitch, which means how many teeth or how much bigger the sprocket gets based on how many teeth it has. It's a little bit confusing, but essentially, if the diametrical pitch is 20, if you have a 20 tooth gear and a diametrical pitch of 20, you will have a sprocket or a gear that is exactly 1 inch of a diametrical pitch. So if I do 20 teeth divided by a diametrical pitch of 20, I end up with 1 inch. And if I do 10 teeth divided by a diametrical pitch of 20, I get 0.5 of an inch. And taking the distance between those two like this will give us that center to center distance that we're looking for. And we're going to go more into this as we actually start designing robots and such. But hopefully this will get you familiar with it. There's really good videos online about this kind of stuff as well if you want to learn some more about it. My model here doesn't do it quite justice. In fact, there's a link that I have in my other email account that provides an absolutely awesome kind of like animated view of gears and how they work. And I'm going to share that with you before everybody goes. Where is it? Where is it? Here it is. Let's see. This is it. Yes. Fantastic. So I'm going to share this page with you. You guys can look over it on your own time. Absolutely fantastic. It explains this stuff with animated visuals. I'll pull the page up over here just so you can see it as I scroll through it. With animated visuals that describe gear ratios, how they mesh. They have little arrows that show you like where the gears are in their revolution. Just nuts. This guy that built this website is a literal genius. And so I'm going to post the address in here. And you can scroll down and you can see that you can change the speed of things, these little sliders. And then they talk about how to measure the rotational rate of things, and then how the different points of a disc rotate at different speeds. They graph those here and show that they go different distances too. See how they're each going different speeds. And they're showing how things are kind of meshing if they're just two round wheels, and how two objects will rotate the same distance relative to each other, but if one's bigger than the other, it'll rotate less far, so on and so forth. Awesome website to visualize and understand gears at a better level. And I really just recommend, you don't necessarily have to read everything, but even just going through all the sliders and seeing what the different effects of things are is incredibly helpful. So with that, I'm going to finish my class here. Thank you guys for showing up. This is the last one for this week, and next week we will pick back up on Monday. Does anybody have any questions? All right. Is everybody like generally enjoying the class? Are you learning stuff? Do you feel like it's too fast, too slow? Do you wish we did more of one thing and less of another? Any feedback is more than welcome, please. All right, then. We'll leave it at that. Thank you, everybody. Emily, do you have anything else you'd like to say?
I was just gonna say that if you want, we can send out like a feedback form like towards the end of the class.
That would be great.
Like unmute themselves. So, yeah.
That sounds great. If you could send that, and I don't know if you can anonymize this so that people don't feel bad about their own feedback, that'd be fantastic because I'd love to have the feedback. All right.
Yeah. Okay. Sounds good.
All right. Thank you, everybody, and I hope you have a good weekend. Oh, Monday's the 4th of July, isn't it? It is. Is everybody okay with meeting on the 4th of July or no?
I think I'm working that night, but we can discuss that over the weekend, I guess.
Yeah, let's figure that out. My bet is that we probably shouldn't meet on the 4th of July.
Yeah, okay.
Awesome.
So probably not next Monday, and I'll send out an email about that.
All right, perfect. Sounds good. Thank you, everybody. Have a good night.
Yeah.
Thank you.
Yep. Thank you.